Welcome to Textbook Engineering Problem, where we explore complex engineering problems and discuss different methods for solving them. In this video, I'll be breaking down a problem and discussing different ways to tackle it. However, keep in mind that there is no one correct path for some of these solutions, and I encourage you to share your own insights and thoughts in the comments. Together, we can learn and improve our problem-solving skills. So, sit back, grab a notebook, and let's dive into today's problem. Today we're working out of Elementary Principles of Chemical Processes 3rd edition, and we're doing problem number 4.11. The problem statement says, if the percentage of fuel in a fuel-air mixture falls below a certain value called the lower flammability limit, the mixture cannot be ignited. For example, the lower flammability limit of propane in air is 2.05 mole percent, C3H8. If the percentage of propane in a propane-air mixture is greater than 2.05 mole percent, the gas mixture can ignite if it is exposed to a flame or spark. If the percentage is lower than the LFL, the mixture will not ignite. There is also an upper flammability limit, which for propane in air is 11.4%. The mixture of propane in air containing 4.03 mole percent fuel gas is the feed to a combustion furnace. If there is a problem in the furnace, a stream of pure air, dilution air, is added to the fuel mixture prior to the furnace inlet to make sure that ignition is not possible. Part A. Draw and label a flowchart of the fuel gas dilution air mixing unit, presuming that the gas entering the furnace contains propane at the lower flammability limit, and do the degree of freedom analysis. Okay, so here I've got information from the problem statement, lower flammability limit, upper flammability limit, and this is just for propane. It's different depending on the different gas that you're using. I've got the diagram here that they gave to us. So we've got our unknowns highlighted in yellow, and all the other information that we know of plugged into it. They mostly only gave us information about the composition of each stream. This one was a little bit tricky. The first time I read the problem, I thought that they were referring to I didn't actually know what they were referring to as this number, but now I understand that it's they're talking about the exit to the mixer, or what's going into the furnace is at the lower flammability limit. Okay. So we do have information about this stream. Then we do a degree of freedom analysis. We've got 3 unknowns highlighted in yellow. And we have 2 components, air and propane. So we have 1 degree of freedom. Part B. If propane flows at a rate of 150 moles of propane per second in the original fuel-air mixture, what is the minimum molar flow rate of the dilution air? Well, let's do our materials balance. And here you can see they gave us one more process specification. So now we have the additional information we need in order to solve this problem. Okay, for this next part, I've done the material balances. Here for propane, here for air, and then I used the process spec. I've numbered in red the how many equations we have. We have 3 equations, and then I've highlighted in blue here the number of unknowns. Here we have 3 unknowns, so 3 equations, 3 unknowns. We have a system of equations, and the equations are independent, so we can solve the system of equations for the different unknowns that we have. So we have N1, N2, and N3. Okay, it asked us to solve for N2, and we did that right here. So that's the answer to part B. How would the actual dilution air feed rate probably compare with the value calculated in part B? Okay, so the actual amount is probably going to be the actual flow rate of number two, stream two, is going to be higher than the flow rate of stream two that we calculated. And the reason for that is we're in this range right here. And then we calculated how much air it would take to bring us right to the lower flammability limit. Well, if we had any sort of variability in our flow rates, which streams normally fluctuate when you're at a certain flow rate. They don't just stay fixed at one flow rate. They're obviously, in the real world, there's a fluctuation. And so if you go right to the lower flammability limit and you start fluctuating on either side of that line, well, every time you go above the line, you are going to have an open flame, and every time you go below the line, the flame will sputter out. So you'll have this sputtering continuously on and off of the flame. And so obviously the flame will be lit for portions of that time. So in reality, what you want to do is if your flow rate is variable within this range, you want to go well past that range. Not too far, because you don't want to you're paying for this extra air that you're pumping into the stream. So you want to go far enough that you're safe, that you're not going to be sputtering, but not so far that it's a heavy cost burden. Okay, so you want to go away from this, right from this limit edge. Okay, well, that is it for part C and for problem 4.11. Thank you for watching, and I hope you found this video helpful in your problem-solving journey. Remember, there are other routes you can take to arrive at the same correct answer, but I encourage you to leave a comment with any additional insights or questions you may have. Also, if you have any specific engineering problems you would like me to cover, please let me know in the comments. Your feedback is valuable, and I look forward to continuing the conversation with you. Don't forget to like and subscribe for more engineering problem-solving videos. Thanks again, and I'll see you in the next video.